Hi, here's Thiago and I'm going to talk about prime gaps and the crazy sequence of steps. So briefly, what is prime? Prime is when a number is divisible by only itself or 1. So we extract the factors of a number, and if the only factors are the number and 1, then it's a prime. If we find something else, it's not. A visual way to represent that is using this kind of triangle. So you can see using the 2, we just can build the 2 using the 1, also the 3, I cannot build the 3 using the 2, but I can build the 4 using the 2. I can build the 6 using the 3, I can build the 8 using the 2, and I can build the 10 using the 5s, so they are not prime. When we cannot build a number using the previous numbers as factors, then we define them as prime. What's a prime gap? Prime gap is the difference between two successive prime numbers. We cannot do that with the first number, but when we take the second one, 3 less 2 is 1, 5 less 3 is 2, 7 less 5 is 2. We put the prime numbers in order and we calculate the difference between the pairs. Yeah, that's nice. That's generally people extract a lot of features about gaps, and there's some nice questions about that. But let's try to do things different today. Let's try to look to the gaps and try to figure out the primes. We could start with the 2, adding 1, we get the 3, adding 2, we get the 5, adding 2, we get the 7, and so on. So if we were able to find the prime gaps, we could use that to find the primes. But yeah, that sounds pretty hard. So let's try to start with something more simple. Let's try to avoid the even numbers, so just the multiples of 2. So you probably realize if we start with 3 or with any odd number and keep adding 2, we're never going to hit an even number. That's nice, that makes sense. And what the key factors here is you have to start with an odd number and you have to keep adding 2. You can add even 4, but then you are going to jump something. But if you just go 2 and 2, we are going to hit all the odd numbers. Let's give a name for those two numbers. The initial value, 3, and the step is 2. We can move that to a data structure. The initial and the step now are like a JSON-like object. And what we want to get is that sequence from these two values, basically adding the 2 on the initial again and again. Let's define those sequence as data structure with a natural initial value and a group of natural values that we are calling steps. The steps values repeat in cycle, just as we showed the 2, repeating again and again. Now the 2 and the 4 are repeating again and again. I adding 2, then 4, then 2, then 4. A more formal definition is the first value will be the initial plus the step 1. And all the sequence values will be the previous step plus the current step. Now we can get values from that using that calculation. 5 plus 2 is 7, plus 4 is 11, plus 2, 13, and so on. Now the challenge is, okay, I have a sequence that avoids all the multiples of 2, and it will be quite easy to create another sequence that avoids 3. But I want to create a sequence that avoids both numbers, and I just have that sequence that avoids the multiples of 2. So how I can do that? So first we need to define the two key elements that we find before. What is our initial step? In that case, the next prime, the number that we are going to avoid, will be the previous initial step. Then we need to define the initial step of the next sequence. That will be the first step of the current sequence. So 3 plus 2 is 5. The first step of the next sequence will be the 5. Now we have these three key elements: the next initial element, the current step from the previous sequence, and the number that we want to start avoiding. And how we are going to do that? We have to make a shift to left on the steps, but that don't make sense a lot when we just have one element. So we are going to talk about that later. Then you have to multiply the steps by the next prime, but it's not multiply the values and convert the 2 and 6. It's in fact creating 3 blocks of 2, and doing that we are going to calculate the values of those steps, but without the cycle stuff, just one round. So 5 plus 2 is 7, plus 2 is 9, plus 2 is 11. Now that we have that, we can find among those next values which one of them have factors with the next prime, and will be the 9. So we don't want that 9 there. We want to go to the 5, to the 2, to the 7, but then go straight to the 11. So to do that, we don't need to add the 2, go to the 9, and go to the 2 again. Let's add these 2 2's and create a 4. So now we are avoiding that 9, but still getting the 7 and 11. So finally our sequence will be 2 and 4 as steps and as initial 5. And you can see on the result, if you pause the video, that we are not hitting any multiple of 2 or 3. Let's do that one more time. So now the next one will be the first step of the previous sequence, the 7. The next prime will be the initial step of the previous sequence, the 5. And our steps now needs to left switch. The first element become the last. This is important. We repeat that 5 times. We detect when we are hitting the multiples of 5. And we merge those steps with the next step, so we avoid them. And here we go. We have this sequence, and let's see what happens with the numbers from 1 to 100. If we remove the multiples of 2, we reduce our search by half. If we remove the multiples of 3 after 3 as well, then removing the multiples of 5, and when we finally remove the multiples of 7, then basically all the numbers from 1 to 100 except the 1 itself will be primes, because the next prime number after 7 is 11, and the next number that is not prime will be 11 times 11, what is beyond 100. But if we run that in another scope, where we don't do all the values exhaustively. So if take another range of 210 elements and I decide to say, okay, let's filter out all the multiples of 2, then we are going to remove exactly half of the universe. From 210 we are going to 105. Then when we remove the multiples of 3, we remove 1/3 of our universe. And when we remove the multiples of 5, we remove 1/5 of our universe. And also the same with the multiples of 7. And you can see we are removing less and less elements, because it's proportional 1 over the value of the prime. And now that we removed all the multiples of 2, 3, 5, and 7, we have 48 elements. But how many of them are primes? 35 primes. So we have values over there that are not primes, and we'll have to check them. But if you compare our search space here with here, yeah, we remove a lot of noise and we reduce a lot of our data. So sequences are good. We just need to look to the previous sequence to create the next one. So this is a very good feature. We can calculate how many elements we are going to merge and their values. There are some properties on the sequence that I'm going to talk about later that allow us to do that. And with every new sequence, we are able to refine even more our results, removing more and more numbers that are not primes. But yeah, the size of the sequences increased really fast. It's not great, and the computer cost to create the new sequence also increased for every new sequence, and every new feature removes less data, so it's more work to remove less data. In some moment we might think that's not worth. So here the first numbers of every sequence. The first one, as we saw, is just a bunch of 2's, the second one is 2, 4, and so on. And you can look closely, you're going to see on the 6 or on the 8 there are like a diagonal, and if it's hard to see on these small values, when we put like many of them, those diagonals become pretty clear. And if it's still hard to see or understand, I'm going to plot them as colors. So 2 will become black and big numbers will become like close to white, and you can see those diagonals now are very clear. This is the first 900 steps for the first 800 sequence. But if we look closely to the top of the values, we are going to see that noise over there. This is not a bug on the image or something. This is actually the values that are in the beginning very unclear yet. They are not following the trend. The 222, for example, it's not following the trend for sure. It's basically a black line. So to make that more clear, I make a shift on the data. So converting that diagonal in a vertical, and that noise become even more evident. And on this one, I compared the value with the previous value from the previous sequence, and we see if they change it. So if the two sequences are pretty similar, we are just going to see a black, but when they change a lot, we are going to see a white, and you can see close to the zero a lot of white. That's where the change is happening, and after that, all the sequences basically are following the same standard, at least on the first values. Some properties of the sequence: the length of the sequence. The first sequence have length 1, it's just one step, the 2, and the step of the next sequence follow that formula. In the same way, the sum of the first sequence is just 2, and the sum of the next sequence will be the sum of the previous times the next prime. And this is basically a factorial, but just with prime numbers, 5 times 3 times 2. And that is a nice name to that, the primordial. I don't know how to say that, primordial. Yeah, that thing. And the proportion between the length and the size is also curious. So as soon as we start to making the steps going to 2 and 2, we are filtering out half of the data. And as we add more and more filters, we start filtering out more and more data. So that number, it will reducing even more. And sequences are state machines. They are easy to understand when they are small. They are even easy to understand when they are big. The problem is they increase too fast, and all the steps from the previous state machine now are embedded into the new one. So this is hard to storage, and a better way to storage that is as a tree structure. The good thing about the tree structure is we can detect similar nodes and we can dedupe them. So this is a tree structure from that previous state machine. It has exactly the same steps. I can go from A to 4, then to B, then 2, 4, 2, 4, 6 to 6. So basically, if you follow the lifts, you are going to get exactly the same previous values. But then we can take some smart decisions and say, oh, that node B was repeated. I don't need storage twice on my memory or on my disk or something like that. And as those state machines increase, this type of optimization make our code even possible, because those sequences become huge really fast. And also we can save some of that data, like what's the sum and what's the length of those nodes, and use that information to make the search process even faster. So if you are searching for some value that is beyond my sum and the current value, go to the next one. Using this tree structure to save our state machines make the optimization possible, but reading that data become a little more funny. I tried different tools, but that one that I enjoy more was using this graph force. So the state machine that just have the 2 is just a node with the 2, as we would expect. When we add the 2 and the 4, they become a line with the central node that just connect them. Those nodes that are just connecting things, I put letters to make it easy to detect them. And now that we are going to add the 5, I will give 1 second to guess what will be the shape. Triangle, square, is this bug. And yeah, it's funny, it's weird, but I really enjoy that. It's my little buggy friend. It's really funny. When we compare with the 7, then we have this more tree structure, but you still can see the shape of that bug or something basically into every branch of this graph. Let's go a little further to the 11, and whoa, this is something, right? And you can see here it's exactly the same process that we have before. The 2 and the 6. They are all here, connected by some nodes that have some funny letters on them. Okay, I know what you're thinking. What's happened when you go to 13? Let's see. We'll still have the same central node, the A dot, that basically is connecting everything, because despite of this looking like a graph, this is basically a tree structure with a very funny shape. Cool. You probably want me to click on the 17, but I'm going to play a video that I did that before. So I saved my GPU. It's already crying here. Nice. So to recap, sequence can avoid multiples. Sequence can be used to create new sequence and to avoid other multiples. Sequences have some nice properties. Sequence can be used to find all the primes, but probably is not a great idea. But that never stopped us before. Sequence increase in size very fast, and avoiding the size problem creating nested state machines was possible, but probably was also not a great idea. Yeah, thanks, and I hope you enjoy this.